All right, so we're back talking about our quadratic equations, and we're down to using the quadratic formula. The quadratic formula is the never-fail process that will get you to your solutions. A lot of students really like this because it's very methodical. It's a process. You can be guaranteed you're going to get to the answer just following step, step, step. So it works for all types of quadratics, but we first start by being in standard form. It needs to be set equal to 0. All terms on one side, so you get your signs right before you plug it in the formula. So the a term is what's in front of the x squared. That's a. B is in front of the x, and then c is the constant. All right, so we're looking at some practice problems here. Always feel free to pause the video. I encourage you to do that and practice so you're doing the active learning. All right, so on this equation, we would solve by saying a is the 1, b is this 6, and c is the constant. Plugging it into our formula, it says do the opposite of b, so -6, plus and minus to get two answers. B squared is 36 minus 4 times a times c. And that is all over, all the way through the fraction. Notice the entire equation is over 2 times the a value. Next, I would simplify the radical part. 36 minus 4 is times there. That's 4 times 1 times -3. So you want to multiply those together. Feel free to use your calculator also. That will be a plus 12. So 36 and 12 for a total of 48 under the radical over 2. Then we always want to reduce our radical. 48 can be reduced to 16 times 3. The square root of 16 then comes out as a 4. So we always reduce our radicals as much as possible. And then if we can reduce the fraction, we do so. So this is over 2 as well as this is divided by 2. So everything's divided by 2. 6 divided by 2, and it's negative, -3. And then this 4 is divided by 2 for a 2, and then the radical 3 is just there as well. Kind of like a variable, it's tacked on to it for our two solutions to that quadratic. Okay, let's do that again. So number 2. Number 2 is actually factorable. We've seen this problem in this session already, in this section. So you might remember it is factorable, so we could get the solutions that way. But I wanted to show you how it also works with a quadratic formula, whether it's factorable or not. You may not like to factor, so you might prefer to use this method. So let's see how that looks. A is 1, B is -1, C is -6. So the formula says negative b, so negative of -1 makes that a positive 1. It just changes its sign, basically. B squared, make sure you use the parentheses. It's the -1, the number squared. We're going to make it +1. This should always be a positive number when we square the b. Minus 4 times a times c, all over 2 times a. So that becomes, like I said, +1, and then -4 times 1 times -6 is actually positive 24, which we know makes 25. So square root of 25 is a perfect square. That's how you know it would have been factorable, because we're going to get a rational solution. There won't be a radical left at all. It's just a perfect square in and of itself. The square root of 25 is 5. So we get nice rational numbers. And when we do, we're expected to work it all the way out as far as we can reduce it. So we can do this. 1 plus 5 would be 6 over 2, or 3. Then 1 subtract 5 is -4 over 2, which is -2. So there's our final solutions, nice rational solutions. And again, when we get rational solutions, that means we could have factored if we wanted to pursue that method. Okay, number 3. So this one needs to be put in standard form first. So don't forget that little step. It always has to be equal to 0. So I'm going to bring these terms to the left side. Standard form. Once it's in standard form, if it's reducible, maybe we'll see an example like that. If you could divide through by something or clear the fraction or clear the decimals, feel free to do that. Any form of that, the ratio comes out the same answer in the end. But anyway, this is not reducible. A is 4, B is -3, and C is 5. Okay, then we're going to run that through the quadratic formula. Negative of B makes it +3. B squared will be 9 minus 4AC all over 2 times A. So that's 9 minus 36 becomes -27. And so we're going to get an imaginary number this time. This stuff under the radical has a word. It's called a discriminant. The discriminant determines what type of answers you're going to get. And some of your homework questions will ask you, what type of solutions are these? So kind of a throwback to what we did in section earlier when we talked about the different types of numbers that we can do, the different categories or subcategories. So negative under the radical, that's your imaginaries. We're going to get 2 imaginary solutions. Because it's a negative under the square root, that comes out as an I. And then 27 will reduce to 9 times 3. 9 times 3 is 27. And then that comes out of the radical as 3, reducing in any order here. You've got an I, it can be on the front or the back or in the middle, it doesn't matter. But here's what does matter. With imaginaries, we have an A plus BI form that's always required. You have to split the real part and the imaginary part into 2 different fractions here, so it's particular about that. So don't forget, the 3 is divided by 8, 3/8, and this all is divided by 8. I, radical, 3, and 3, whatever order you want to put that in, that's also over 8. So 2 separated answers when you have the imaginary part that you got to deal with. All right, and one more example. Again, please be sure you're practicing these on your own, pausing the video. On this example, I would actually take everything over to the right side. I kind of like my square term to be positive, although it's not a rule, certainly, but I think it's easier when it is. So I'll make it 0 on the left side and move these 2 terms across, making it positive 4x squared minus 12x, and the 11 was already on the right side, so just bring it down as a positive 11. All right, so we've got A is 4, B is -12, and C is 11. Plugging that in our formula, negative B plus or minus, B squared is 144 minus 4AC all over 2 times A. It kind of gets in your mind after you do that over and over. So then we're going to have 12 plus minus 144 minus, let's see, I need to use my calculator. 176 all over 8. 144 minus 176, so I'm going to be in the hole. I'm going to have a -32 for that. So we've got 12 plus and minus -32 over 8. So we've got another imaginary number. So notice that's imaginary, so we're going to have to pull these apart again. But that will reduce. 16 times 2 is 32. So it comes out as a 4 radical 2, and don't forget your I somewhere on that. So that will be 12 plus and minus 4 radical 2i all over 8. Then lastly, we have to pull those 2 answers apart. 12 is over 8. We'll reduce that. And 4 radical 2i is over 8. These do reduce. The 12 divided by 8 will reduce to, let's see, what does that reduce to? 4 into 12 is 3, and 4 into 8 is 2. And then the 4 and the 8 reduce to a half over 2, like that. So that would be our final form of that answer. All right, again, you can just practice using that quadratic formula till that just comes real second nature to you. So if you need more problems to practice, there's so many of them in the study plan, as well as the one that I've assigned. I try not to assign so many that it overwhelms you, but you may need to practice that more than what I've provided. So if so, go to the study plan or even go to your textbook, your e-text. You can go there and work some various problems, and the answers to the odd ones are in the back of the book. And so you'd be able to find some more to kind of practice through till you get just so good at that. It's kind of fun once you get the hang of it, I think. All right, one more thing. We're going to talk about third-degree equations. If we had, mainly we have these quadratic equations that we've been focusing on, second degree, and then we have the linear equations. Most of the algebra we do is either going to be linear or quadratic, but every once in a while we have these other types of equations. So one example is this third-degree equation. We have a special method for some third-degree equations, not all, but if it is such that these two things are perfect cubes, we have a pattern for that. You'll see the pattern is listed in your notes. When you have the sum of cubes, perfect cubes, you take the cube root of each of these. That's x and y in this case. Then you square this, times these two together with the opposite sign, and you square that. You could multiply all that out and see that it's so. If you distribute this x, let me just show this to you real quick. You don't have to do this, regularly, but this distributed minus this times this, and then that times that. Then distributing the y times that, running out of room there, then y times the last thing. What you'll find is a lot of the terms cancel out. This matches up with that, and this and that one, they're opposites, and it gets you right back to x cubed plus y cubed. So it works. It's just a weird little formula. I wanted to convince you there really is a reason to this. It works. This factors to that. Also, if you have a minus cubes, there's a pattern for that as well. All right, so only then do we have a way to solve these third-degree equations. So back to our example, these are perfect cubes. So we find the cube root. Cube root of x cubed is x. The cube root of 8 is 2. Then the pattern says we square this cube root, times these two together with the opposite sign, and square that cube root. So it factors a little bit, but it factors just enough to help us solve this, because this is a quadratic and that's a linear. We know how to solve those two things, so it helped us along. We set each factor equal to 0, and then solve each part. The first one is linear, so it solves by just moving the 2 across the line. And the next one is a quadratic, just what we've been doing. We'll have to run it through the quadratic formula, and we can do that. So let's say we did that, and the solutions for that were 1 plus and minus I radical 3. So you'll notice there are 3 solutions. 1, the real solution, and then 2 imaginary solutions for a total of 3 solutions. So it does work. One last example, I'd like you to try that now. Do a cube with a minus in it. It's going to be pretty much the same, but the signs mix up a little bit. So again, with the formula, it says when you have the difference of cubes, or as long as they're both perfect cubes, you can start out with their cube roots. So that's x and 3. Square, times together with the opposite sign, and square. And again, you could see that it's so. If you multiplied all that out, you could distribute this, combine the like terms like I showed earlier. It just works. It's a weird little pattern, but it does work. So you've got those formulas there. Follow that. Again, it only works when we have perfect cubes. Then you set each factor equal to 0 by that 0 factor property that we talked about earlier in this section. You get one real answer. The x is 3, the linear answer, and then we've got this quadratic we have to solve. So we can run that through the quadratic equation, and this always gives us 2 imaginary solutions for the other 2 answers. you know, that's fine, but they still are solutions to account for. Since it's third degree, we're looking for 3 answers. So we get square root of negative 27, again, because it's imaginary. I think we did one very similar just earlier. We did the square root of 27. It comes out to be 3i and 3n. And then we pull that into the the a plus bi form. All right, I hope that helps. Contact me if you have any questions, and I'll catch you on the next video.